Good morning, students. Welcome to Complex Analysis Live Lectures. In this class, we'll discuss about some of the examples of contour integral, and we will see an important inequality called ML inequality. Okay. So, if we last class we have discussed few examples. So let's have another example. So consider, let C be any smooth curve, or you can call it smooth arc, okay, and f of z is equal to z. Okay, then we want to evaluate, so we want to find the value of f of z over c, okay, uh, where the c is, you can say, let me write this solution. So let c, which you can write as z of t, okay, where t is varying from a to b, okay, is a arc, okay, starting from z1, okay, which is nothing but z of a, to z2, which is nothing but z of b. Okay, this is a, if we take this as c, then we want to calculate f of z over c, where f of z is equal to z. Okay, so we know already integration of c f of z dz is nothing but this integration of a to b f of z of t into z dash of t d, right? So in this case, what is our f of z of t? This is nothing but simply because it is z, so it is z of t into z dash of t dt, right? But we can observe that this is nothing but the as differentiation of z of t, okay, whole square by 2. This one is nothing but 2 times 2 to 2 will get cancelled, is same as z of t into z dash of t. So yesterday whatever result we have seen, therefore this integration of a to b, whatever function we have, z of t into z dash of t dt, is nothing but this z of t square by 2 and limits from a to, okay, that small wt and capital wt which we have discussed. So this is same as z of b square, okay, minus z of a square by 2, right? But what is our z of b is nothing but z2, and z of a is z1, therefore this is nothing but z2 square minus z1 square by, therefore this is the integration of our f of z, this z dz over c. Okay, now that means whatever smooth curve we take, okay, this value whatever we are having right hand side is only depending on the end point. Okay, so we can have some observations here. This example compared to other example last time what we have discussed is that the value of the integral, first of all, integral is independent of the path, independent of the path we choose. What is matter is, what it matters only on what are the end point, right? Whereas if you see in last class, whatever example we have discussed for this contour integral, yeah, for example, you see this here, f of z is this function, and you have o a b o, this is one, or you take o a b, which is 1 c1, and the other one is c2, which is like, okay, we have observed that this, if over c1 the integral value is different, and over c2 the integral value is different, because if they are same we might have got the value is 0, but we didn't get value as 0, so therefore those integrations are different over c1 and over c, right? But whereas for this function what we have seen, this example f of z is equal to z, this is independent of the path, right? Now the second observe we can do is, even if our curve c whatever we have taken, even if it is not smooth, that means even if c is, so even if C is a contour. Okay, that means containing finitely many smooth curves. Okay, then also result is true. That means it depends only on endpoints. Say the C is so each ck, so this C is a finite combination of this ck end to end. So where each ck is a arc, so you can call it smooth arc with endpoints with endpoints. That means starting and end. Okay, with endpoints zk and zk plus 1. Okay, then integration of f of z dz over c is summation of integration of our f of z is z. So dz over ck, the k is from 1 to n, finitely many, so n if you call it. Then this is nothing but summation k is equal to 1 to n. Each one we already calculated from this smooth arc. Okay, so zk plus 1 minus zk square. Okay, so this is nothing but zk plus 1 square minus zk square by 2. But if you expand this summation, what you have here is only first one and last one will remain. That means zn plus 1 square minus z1 square upon 2. Right? Fine. So if you have a curve, something like this, okay, so with endpoints, z1, z2, z3, they can call it z4, z5, and so on, zn or zn plus 1, then you split into this and sum up, you will get. Okay, this is your entire contour C. Then also, okay, now as a third one, we can observe that if C is a closed contour, that means endpoints are same, then obviously what we'll get is integration of this z dz over c. This value, because endpoints are same, so we get this value is 0. Remember, in last class the example whatever we have discussed, even though it is a closed one, but that integration is not 0. Okay, so it depends on what function. In next class we'll see which type of functions f of z for which integration of c f of z dz is 0 if when c is a closed one. Okay, that we'll see in next class. Fine. Let's take another example which involve that contour contains a points which are points on the branch. Okay. So let's see how we can deal with this contour integration whenever branches are there, your functions are branches, and some point of that contour is there on the branch. Because if some point is there on branch cut, that function is not continuous at those. Okay. So let's take one example. So evaluate integration this z or half, which is we know the multi-valued function. Okay, where what is this c? C is a semicircular path. Z is equal to 3 into e power I theta, where theta is from ranging from 0 to pi. Okay, and this is with starting from z is equal to of course 3 to z is equal to minus 3. Okay, so I can draw that also so that we can understand. So that picture is, because this has a z power half has a branch. Okay, now say this is 3, then you have this is your c. Okay, this is 3 and this is minus. Remember, because this is a branch cut, so whatever you are having here, this is branch. Okay, and your point this z is equal to 3 is on branch cut, and which is also a point of this contour. Okay, so at that time how we can evaluate, so that is possible. The main reason is we can have solution. The main reason is whenever we want to evaluate integrals, we require that that function is, it is enough if that function is piecewise. Okay. So here this z power half, Okay, this is one of the principal branch. If you want to write that, where z power half is equal to, of course we know it is exponential of half into log z, where this mm, this is greater than 0 and theta is between, argument of z is between 0 and 2. Okay, so you can call it this principle, right? So how we can calculate is that the only problem is this function z power half is not defined at 3 because the tree is on branch cut. Okay, you can say it is not continuous. Okay, but we can make sure that this f of z. So our claim is this f of z, which is z power half, is piecewise continuous on this given contour C. Okay, there is no problem for all these points. Only we have to check at this point 3. So it is enough if we show that this limit, one-sided limit, exists at 3. Okay, then it will become piecewise continuous. Right? Okay, that is not a difficult one because let's try to find out what is this z power half. Okay, so this z is 3 into e power I theta. Okay, this implies, what can we say about, and if you write f of z as z power half, then what is f of z of theta into z dash of theta? Because we want to find this one. So f of z of theta is 3 power half. Okay, uh, this you can write it here as exponential of half log z, right? So this is exponential of half into log z, which is log 3 into e power I, okay, into z dash of theta, which is same as 3i e power I theta, right? So this is same as, if you multiply this is exponential of uh, log 3, natural logarithm of 3. Okay, that means half into natural logarithm of 3 plus this is log e power I theta, that is same as I theta into 3i e power I theta. Okay, remember this is half. Okay, so this is same as e power this root 3, because this is exponential. If you take, then this is nothing but root 3, because natural logarithm and exponential will get cancelled, plus it is e power I theta by 2, but not plus, multiple, because it is exponential. Okay, then what we have here is 3i e power I. Okay, fine. So this is same as 3 root 3 I e power I theta by 2. Okay, plus 3. That means you can call it 3 theta by 2. Okay, so this is your f of z of theta into z dash of theta. If you write this as 3 root 3 into cos 3 theta by 2 plus uh, I sin I sin 3 theta by 2. Of course, here I is. Okay, so that means if you multiply, if you take in I inside, this is 3 root 3 into I square is minus, right? So this is same as minus, okay, sine 3 theta by 2, okay, plus I times cos 3 theta by. Now you can check that the only problem is that theta is equal to 0, because when z is equal to 3, this becomes theta angle is 0. Okay, so this, whatever you are taking here, this is continuous, there is no problem, right? This is continuous for theta between 0 and pi. Okay, 0 and pi, but only problem is when theta is equal to 0, that means at z is equal to 3, you can check that the right hand limits of this real part and imaginary part. When theta is equal to 0, this real part limit is 0, and imaginary part limit when theta is equal to 0, this is 1. So then this constant is there, which is 3 root 3. Okay, So therefore, also right hand limit of this f of z of theta into z dash of theta at theta is equal to 0, okay, exists, okay, for real and imaginary part, which are obviously, what are they? For real part it is 0, and the imaginary part it is this is 1, so you have 3 times root. Okay, limits are 0 and 3 root, right? So therefore, by defining this function f at theta is equal to 0 as this I times 3 root 3, okay, then we know that this, therefore this f of z of theta into z dash of theta is piecewise continuous on this entire one theta, this, okay, right? Therefore we can calculate this integration. So therefore integration of f of z dz over c is nothing but integration of 0 to pi, okay, f of z dz z dash of theta is nothing but this 3 root 3, 3 root 3 will come outside, okay. What we have here is minus sine 3 theta by 2 plus I times cos 3 theta by 2, okay, d, right? So you simplify this and I'll in that calculation you can easily do it. This is finally, of course, either you write like this or you simply, this is same as 3 root 3 I, uh, just to understand we have expanded this, you can put it in this way one, 3 root 3, okay, into I e power I theta by 2, okay, e power I 3 theta by 2 d theta, and simplify this, what you will get here is minus this, what you will have here is 2 root 3 into 1 plus I. Just verify this, okay, fine. So this how you can have, even if a contour contains a point which is on the branch cut, still we can calculate, because to evaluate integration we require only that function is piecewise continuous. Okay, fine. I'll give some exercise to find some more examples, okay, and see whether you can do it or let me take that. Okay, so I these are the following exercise. Okay, you please go through it and try to find the this contour integrity. Okay, fine. Now next what we will see here is about the, I can say, upper bound. We can give upper bound for moduli of contour integration. Contour integration. That means we will try to give something like, so what is the meaning of this? If we have integration of f of z dz over c, then what can you say about, can we give some value, what is this one, so that you have a maximum value. This inequality is useful when we calculate further integrations in later. Okay, so to do it, we'll start with one lemma, and from that lemma, uh, this result follows, it is called ML inequality. Okay, so first we'll start with the lemma. Let W of t, okay, be a piecewise continuous complex valued function, complex valued function defined on t, which is say from a to b. Okay, then the integration of this W of t dt from a to b, and absolute value of this is less than or equal to integration of a to b modulus of W of t dt. Okay, that means you can take this value is less than or equal to integration of absolute value of W of t. Okay, let's prove this. It is even though it is lemma, you can easily solve this by considering as a problem. Okay. So first of all, we can observe that if this integration of w of t from a to b, if this is 0, then we are done already. We don't need to prove anything, because what we have here is this will 0, and what we are having here is a greater than or equal to 0. So we know already from real calculus is that if integration of a non-negative value is always non-negative. Okay. So assume that integration of a to b w of t dt is none, which is a non-zero complex, right? So because it is a non-zero complex number, so we can represent this in polar. Okay. So let this integration from a to b w of t dt is, call it some polar form. So r naught e power I theta, right? Now this you can simplify and just make some calculations. So that means if I take this here, that for a naught, r naught will become w of t dt e power minus I theta. Okay. This you can bring it inside. That means e power minus I theta w of t dt, which is r naught. Remember, this r naught is a real value, right? And this integration have complex as well as this real as well as imaginary, right? So this implies this r naught is same as real part of whatever we are going to get here, real part of this integration, right? Because since r naught is real, okay, right? But we have seen in last class, this is same as integration of the real part of this function, which is e power minus I theta into w of t. Okay. But observe, a basic thing is, as real part of any function is always less than or equal to absolute value. It's absolute value, right? But this is same as modulus of e power minus I theta, which is 1. So you will have modulus of w, right? This implies r naught, which is nothing but integration of a to b real part of e power minus I theta. Uh, so we have to write here I theta naught, right? This is I theta. I theta. Okay. Fine. W of t dt. But because this is less than or equal to this, so therefore this integration is also less than or equal to modulus of w of t dt, again by from real calculus, what we know already, right? So therefore r naught is less than or equal to this here. But now if you take this one here, here, so if you call it this as a star, so by star, if you take absolute values both sides, this value is simply right hand side is r naught, okay, and what we have here is modulus, right? By star, what we have here is r naught. That means r naught into e power I theta naught is absolute value of integration of a to b w of t dt, right? But this is same as r naught is equal to absolute value of integration of a to b w of t dt, right? Now by combining these two, what you will get here is, therefore if you combine this a and b, therefore by a and b, what we have here is modulus of this integration, okay, is less than or equal to integration of mod, right? So it is very simple one. Now using this lemma, we can prove a result, what is called is inequality, called, you can call it as ml inequality. Okay, fine. So what it says is, we'll write this statement and we'll try to understand. So let C be a contour, C be a contour is defined contour of the length L, capital L. Okay, and suppose f of z, okay, um, is piecewise continuous, piecewise continuous on this C. Okay. Now, if there exists a real number m greater than 0 such that mod f of z is less than or equal to m for all z belongs to C, at which this f of z is defined. Okay. So wherever it is not defined, you can forget about that point. So then integration of f of z dz over C, and you take the absolute. That means modulus of this integral is less than or equal to m times. Okay, so that's why it is called ML inequality. So whatever that modulus of f of z, whatever upper bound for f of z times the length of this contour. Okay, fine. So proof is not difficult one, because our curve z, which is z of t, right, where t is from, say you can call it from a is less than or equal to t is less than or equal to b, which is, you can have z, which is starting point, and z, right? Then yes. Therefore, with this, what we know is that integration of f of z dz over c, right, which is nothing but how we have defined, this is nothing but integration from a to b f of z of t into z dash of t, right? So whatever you have here, whatever we are having here, this we can call it as w of t, just like for this lemma, this we know it is piecewise continuous, right? So therefore, by previous lemma, what we know is integration of this mod c f of z dz, this is nothing but absolute value of integration of a to b f of z of t, okay, into z dash of t dt. By previous lemma, this is less than or equal to integration of a to b mod f of z of t, okay, into mod z dash of t dt. But we can observe that as mod less of z, okay, is less than or equal to m, and c is nothing but z, which is z of t. So what we have here, this one is actually less than or equal to m, right? So therefore, what we are having here is integration c of dz is less than or equal to m times integration from a to b mod z dash t. But if you remember, what is this one? So whatever we are having here, this is precisely the length of the contour. Therefore, we have this, right? So the absolute value or an upper bound for the contour integration is nothing but the m, where m is the upper bound for this f of z, times the length of the contour. Okay. Yes. So we can quickly have a remark. One may ask, what is the guarantee that such m exists? So this m exists by a real case, whatever we know, because mod f of z, which is a real case, right? So assume that if f is continuous, then mod f of z is less than or equal to m on this a to b, that means closed interval a to b. Okay, so the m in above lemma exists because, say first, if f given whatever f of z, if f of z is continuous, or you can say it is real, is continuous on some a complete, then what we know, by real case, any real function which is continuous on a closed and bounded interval, then it attains its maximum. Okay, then this mod f of z has maximum value. Okay, now even this, even if f of z is continuous, okay, then that means this mod f of z, you can have a that curve contour, okay, you can break it into finitely many, where in each part this mod f of z will become continuous. Okay, so that means what I'm saying here, So if you have something like this, okay, this is piecewise continuous, right? So you can call it, this is like A1, then A1, B1, or A1, A2, A3, and some AN. Okay. Now here each part, your f mod f of z is continuous. Okay. So there exists some M1. So there exists some M1 here, there exists some M2 here, and so on. There exists some M. Then take the maximum of this. So at this case, your M is maximum of this M2. Okay. So whether mod f of z is continuous or piecewise continuous, by using the known result of real analysis, we can guarantee that such M exists. So we can have always, we can find an upper bound for the moduli of this contour integral. Okay. So let's see one example so that we can understand. Let me take show that the absolute value of integration of c f of z, which is z plus 4 upon z minus 1 dz is less than or equal to 6 by 7, where what is your c? C is an r, okay, of the circle. The circle mod z is equal to 2, okay, starting from z is equal to 2 to z is equal to 1. Okay. Of course, that lies entirely in the first quadrant. If you want, you can draw that picture. Okay. Part of this circle is 2 and this is 1. This is C, right? So we want to show that when you have c and then you have f of z, then this maximum value of this one modulus is 6 pi by 7. Okay. Fine. So how we can do, whenever we want to find in this two things by using this one, we require m and l. What is the m? M is the maximum value of mod f of z. Okay. So if your f of z has numerator as well as denominator, then we will find the maximum value of numerator and minimum value of denominator and that c, so that you will have maximum value of this entire ratio, okay, fraction. And also we will find the length of that contour, okay, for this c given c, right? Fine. So here given that mod z is equal to, so given is that mod z is equal to 2. So therefore we want to calculate. So let your here f of z is equal to z plus 4 upon z cube minus 1. That is our f of z. We want to find, so we want to calculate m. That means we want to find m such that mod f of z is less than or equal to m. Right? So what is mod z plus 4? By triangle equality, which is same as mod z plus 4. So therefore mod z is equal to 2. So this is less than or equal to c. And as I said, when you have a denominator, then we will try to find the minimum value. So which is same as mod z cube minus 1, right? Of course, you will have modulus of this. Okay, but here it is positive. So this is 2 cube, which is 8 minus 7. The 8 minus 1, which is 7, right? So therefore, mod f of z is z plus 4. Z cube minus 1 is less than or equal to, this is 6, and 1 by this one is less than or equal to 7. So you have 6 by 7, right? Obviously, now what we is remain to find is the length. Okay, L, which is nothing but integration from value of z is from 2 to 2i, right? Then we want to find the length of the contour, so which is z is equal to 2 mod z is equal to 2. So which is, you can say, so this is from a, you can call it from a to b, z dash absolute value of z dash of t, where c is z of t, where t is from a to b, right? Now what is our given c? Our given c is the part of the circle. So here our c is mod z is equal to 2, starting from z is equal to 2 to z is equal to 2i. So we want to convert this into parameterization. Okay, so this z can be written as 2 times, because radius is 2, so e power I theta right? Where theta is from where to where? So theta will vary from 0, because when theta is 0, you will get 2, and when theta is pi by 2, you will get value as 2i, right? So therefore, what is z dash of theta? So this, if you want, you can write it as z of theta. So therefore, z dash of theta is 2i e power I theta. This implies the L, which is the value is from 0 to pi by 2, and modulus of z dash of theta d. Okay. Therefore, this is same as 0 to pi by 2 modulus of 2i e power I theta d theta. So this modulus of I into e power I theta is 1. So 2 will come outside. Then what we have is pi by 2 minus 0. So therefore this is pi. So our L is pi and our M, this maximum value is 6 by 7. So therefore modulus of integration of z, okay, dz is less than or equal to 6 pi by 7. Okay, fine. We can also use the advantage of this one is that let's write that example. So we can, without evaluating the integral, sometimes we can show that the limit tends to 0. Okay, so second example, see, so let me write that without actually evaluating the, or finding the value of the integral, um, show that, so show that limit of integration z power of 1 z square plus 1 dz r as r tending to infinity is 0, where what is this CR is the semicircular path, is semicircular path that is equal to r into e power theta, where theta is from 0 to pi. Okay, and this z power half, because it is a multi-valued function, so we should mention what is the uh, one single value. So is the branch is the branch is one of the branch, you know, given by exponential of log z. Okay, this, if you want, you can write this as r into e power I theta by 2. Okay, where your r, capital R, okay, this capital R is greater than 0, and theta is between minus by 2 to 3 pi. Okay, that means this principal branch, we know theta is from alpha to alpha plus 2 pi. So here our alpha is minus pi. Okay, fine. Proof is not at all difficult. By using the inequality, we show that modulus of this value is, okay, and then we will take the limit of it. That will be tends to 0, right? Fine. So here, because our z is given to be r into e power I theta, where theta is from 0 to pi, so therefore what can you say about modulus of this z power half? Okay, this is square root of r, right? Because modulus of e power I theta by 2, so modulus of e power I theta by 2, which is 1. So this is not, okay. Similarly, what can you say about mod z square plus 1? Mod z square plus 1 is greater than or equal to mod z square minus 1. Okay, but this is same as um, this is equal to r minus 1. Okay, as absolute value, if, right? Okay. Now that means this, whatever, if you call it this as f of z, therefore mod f of z, therefore modulus of z power half by z square plus 1 is less than or equal to root r upon r square minus 1. For convenience, you just call it this as mr. Okay, fine. Now you can find the length of this curve. Okay, what is the length of this curve? So L is how we can represent again, because this z is r into e power I theta, where theta is from 0 to pi, right? Therefore, what is, I can write L is from 0 to pi um, modulus of z dash of theta dt. Okay, so our z of theta is r into e power I theta. So if you find z dash is r I e power I. Okay, so this is integration from 0 to pi r e power I theta dt. Okay, so therefore this modulus, this value is 1, so what you have here is r. Okay, so therefore the integration of this over CR modulus of, okay, this one is z power half 1 square plus 1, this dz is less than or equal to mrl, so which is mr is this root r upon r square minus 1 into r. Okay, now you can simplify this right hand side. Okay, this right hand side, if you simplify, you take out r, here r square common. Okay, so that means you take r square, it is 1 minus 1 by r square. Here I can write this as r power 3 by 2 into pi, right? So if you write this as that means if I multiply by this root r and root r, okay, and now take limit as r tending to infinity. This is same as pi upon root r, because r root r is not there. Then 1 by 1 minus r. Now as r tending to infinity, this part will tends to 0. So you have 1 here, and this part will tends to, because it is in denominator, this part tends to infinity, right? Therefore, limit as r into infinity, right? Integration of CR, because this absolute tends to 0, right? Therefore, that has to be 0. Z power this tends to 0 as r tending to infinity. Therefore, z power half plus 1. This value is, here we have used the ML inequality is that, right? Okay. So take some exercise and solve those problems. And if you have any difficulty, you can ask. Okay. So these are the exercise problems which have been taken from the textbook. Okay. So try to solve these problems. Okay. And if you have any difficulty, you can ask. Okay. I am ready to help. Right. We'll stop here and we'll see another interesting properties next.